So the next section we're going to go over is 11.6, which is on conditional probability. So we've kind of seen a little bit about this before when we did the probabilities without replacement. So the first event happened. Now your second event depended on what the first one happened. So we had to change how we calculated that second probability. So this is kind of conditional probability on its own. So in general, the probability of event E2 occurring, given that event E1 has happened or will, is called a conditional probability. So we write this in a specific way. So you want to calculate the probability event E2 happens. This bar indicates given that event E1 has occurred. So the way you kind of read this is the probability of E2 given E1. So let's kind of see what we mean by that in an example. We've got all of these different shapes, triangles, squares, circles, and each shape has a number inside of it. So we're going to assume each figure is equally likely to be selected at random. So kind of you put these shapes in a hat, you're going to pull out one of these tokens. So we want to determine the probability of selecting a circle given that an odd number is selected. So basically I'm calculating the probability this event is occurring knowing that I've already selected an odd number, okay? So since I've already selected an odd number, it narrows our choices down a bit. I selected odds, so this is a possibility, this is a possibility, the 5 and the 7. I now get to ignore these other ones because they're not odd numbers. So I'm given an odd is selected. So an odd number was selected, it narrows our choices to these 4 options. And we want to see now, based on these 4 options, what's the probability that we have a circle? Well, 3 of 4 of these are circles. So I've narrowed down my choices a bit. I know I now have 4 possibilities because an odd was selected. So the probability that we pick a circle, given that an odd number was selected, is 3 out of 4. So the 4 comes from the fact that I have 4 options left because it's an odd number. And then from this, if we want to see how many are circles, 3 of them are circles. So now I know it's odd, I've got 4 options, and it narrows my choices down to 3 out of 4, okay? So now let's try it again. We're going to see kind of the reverse of this. What's our probability of selecting an odd number given we've selected a circle? So now instead, I've selected a circle, so I've picked one of these 3 choices, okay? So since a circle was selected, my only remaining options are 1, 5, and 7. Well, all of these are odd. So if we know we've selected a circle, the probability that it's going to be an odd number is 100%. You have definitely selected an odd number because I've gone through and I've selected these circles for sure, okay? So the probability for any 2 events E1 and E2 occurring is given by this notation. So the probability of event E2 given E1 has occurred. We're going to calculate this in a specific way. E1 has occurred. So now my denominator purely becomes the number of events that make E1 successful. So I've narrowed my pool down because I know E1 has happened. Then in the top, I'm going to look at kind of the overlap between the 2. So if you look back to these examples, I had 4 options for the odd number. And then from that up top was the probability that it was odd and a circle. So 3 of those options remained. So our conditional probability is given by this formula, where what goes up top is the sample points that are common to both events. And in the bottom, it's the sample points common to just event E1 occurring. So another way you can kind of think of this with our intersect notation is we want the number of events that are common to E1 and E2, so it's the intersection of those, over the number of events that make E1 successful. Okay? So let's go through an example. We've got the following results for a coffee taste test given in this chart below. So we've got different classifications of people. They either fall into the men or women category, and then they're going to pick that they prefer Dunkin' or they prefer Starbucks. So we have a bunch of different outcomes for each of these. So 60 men prefer Dunkin', 40 men prefer Starbucks. In total, we have 100 men. So now from this, if one of these individuals is selected at random, we're going to determine the probability the individual selected first just prefers Starbucks. So if we look at the prefers Starbucks, 115 people in total like Starbucks out of 225, okay? So the probability that people prefer Starbucks is 115 out of 225. So the probability that this single person we pick out like Starbucks is 115 out of 225. Or if you do go ahead and simplify that, it becomes 23 over 45. So start by dividing by 5 and see if you can go any further from there. Okay? Now we want to see if we pick this one person at random, what's the probability that the person selected is a woman? So if we go back to our chart and we look at the woman row, in total there were 125 women out of, again, a total of 225 people. So the probability that the person is a woman is there's 125 out of 225. If you divide each by 5, you get 25 out of 45, which you can divide by 5 again to get the simplified form of 5 over 9. Okay? So now we want to get into this conditional probability. We want to see what is the probability that the person prefers Starbucks given that we definitely picked a man. So we know the individual is a man. What's the choice we like Starbucks? So now my total changes a little bit. We know it's a man, so I only have 100 possible people I'm picking out of. And of those, 40 of them like Starbucks. So it narrows our selection down a little bit. The probability this person prefers Starbucks, given that it's a man, is we look at a fraction. In the bottom, we narrow our selection down because we know it's a man, so I'm going to look at how many men there are in total. And up top, we want the number of individuals that like Starbucks and are also a man. So we've narrowed our total down. I know it has to be one of these 100 people, and 40 of them like Starbucks. So the probability this person prefers Starbucks, given it's a man, is 40 out of the 100, which you can simplify, divide both by 20 to 2 over 5. Okay? Next, we want to look at the probability that the person is a man, given that they prefer Dunkin'. So now what this does is we want the probability of a man, given they prefer Dunkin'. In the bottom, we're narrowing our choices down and we just want to see how many people prefer Dunkin'. And then in the top, how many of those that prefer Dunkin' are men. So now they prefer Dunkin'. My new total group is out of 110. And we want to see what's the probability they were a man. Well, 60 of these 110 were men. Okay? So up top, we have 60. The number of people that like Dunkin' is 110. So we can simplify that. There's a 6 in 11 chance. All right. So let's try one more with this example, we want to see what's the probability that the person is a man given that they prefer Starbucks. So same type of thing. Now we just know that they're Starbucks. So in the bottom is going to be our total for how many like Starbucks. So it narrows our selection down a little bit. We know they prefer Starbucks, so it's got to be narrowed down to 115 individuals. And from that, 40 of these were men. So our probability is going to be 40 out of 115, which if you divide by 5 becomes 8 out of 23. Okay? So the whole idea is you know this first event has happened. In these previous examples, I had my total population was 225, but it narrowed down my population to a smaller group of individuals. Okay? So let's try one more. A hat contains 4 bills. One of them's $4, $5, $10, and $20. Each bill is equally likely to be selected, and then 2 bills are going to be selected with replacement. So I'm going to draw from this hat. I'm going to pick out one bill, see what it is, and then I'm going to put that bill back and then draw it again. So first thing we want to do is we want to construct a sample space. So remember, this is kind of like a tree diagram that will help us out. So I'm going to first select a bill. I have 4 choices to choose from. Then I'm going to put that bill back and then pick a new one. So I still have 4 more options. So there's 4 possibilities for the first event, 4 possibilities for the second. In total, there are 16 possible outcomes for this experiment. So if we want to create a sample space, a tree diagram is going to be really useful. So the first thing is I've got my first round of selections. So at first I could pick $1, $5, $10, $20. Then on my second pick from this $1, I could pick any of those options again. If I pick $5, I can pick then a 1, 5, 10, or 20 in the next one. Same thing, if I pick a 10, I've got 4 possibilities, and a 20, I've got 4 possibilities. So our sample space becomes these possible outcomes. We have 16 of them in total. So in here, you select a 1 first, and then select a 1, a 5, a 10, a 20. So it keeps going in that pattern. So now that I have my sample space fully constructed, we want to go ahead and determine the probability that both bills are $1. So not only my first selection has to be a 1, my second selection has to be a 1. So really, I only have one possibility that satisfies this. The first one being a 1, the second one being a 1. So the probability both bills are $1 is 1 out of 16. One option allows you to select $1 twice. Now we want to figure out what's the probability both bills are $1 given that we definitely did select a 1. So what we've done now, I know I've selected a 1. These options are completely wiped out. They don't matter. I selected a 1, so I've narrowed my options down to 4. I've got to be in one of these cases. Okay? So now, knowing that I've picked a 1, the probability that I get a second one is 1 out of 4. Okay? So the way you can kind of think of this is you want the probability that we select $1 given that we selected $1. So up top would be the probability, the number of events of getting a 1 and then a 1. And in the bottom are the number of events that allow us to select a 1 in the first one. So you really have a 1 in 4 shot. So I've gotten rid of all of these options, and the only 4 that remain are up here. So I have a 1 in 4 chance. Okay. Now for our last one, we want to see what's the probability both bills have a value greater than $5, given that the first bill is a 10. So we know we've selected a 10, so I can get rid of these options. I can get rid of these options. I can get rid of the 20 as well. I definitely selected a 10. These are my only options that remain. So now my bottom is going to be 4 possibilities. And we want, what's the probability both bills have a value greater than 5? So I've gotten a 10. I could get a 10 in the second one. That gives us both of them being bigger than 5. Or I could land in this option. I get a 10 and then a 20. Both bills are bigger than 5. For these two options, the first bill is bigger than 5, but then we fail in the second one. These aren't bigger. So really 2 of these 4 remaining satisfy that criteria. So the probability that this bill is greater than 5, given we've got a 10, is 2 out of 4, or really just a half.